Okay, we'll start now. So just recapping the finite volume method for the collocated grids. So we discussed when we talked about the predictor equation discretization. So there we applied the finite volume method. So we wrote terms in the form of flux terms, right? So we got the convection flux, as we see here. Then we had the diffusion flux, which basically is given by nu times the grad u dot delta gamma sound over the complete phase. Then we had the pressure term, and then finally we wrote this equation in the form of. So this form is sometimes also called a semi-discretized form, because we still haven't given you the discretization for these terms such as UF, the flux, mass flux F, or the diffusion flux F. Right? So the next step is to write what sort of approximation we need for these terms, and then once you do that, you get the final discretized form. So this is called a semi-discretized form, because this equation gives information about the discretization of the transient term, as well as it tells you at what time are we discretizing these terms such as the flux term, the u term, and so on. So this has some information. This is not the governing differential equation. This is not even the final discretized form, so we call it the semi-discretized form. So this was written for the collocated grids, where everything was calculated at the center of the control volume for common control volume for pressure and velocities as well. So let's write this for our staggered grid that we discussed yesterday, day before yesterday. Just to recall that we had this control volume where capital P was center, which is used now for, so this control volume center is for pressure, and then we have the x velocity, which is defined on the faces here, and then we have the y velocity, which is also defined on the faces. So the control volume for the x momentum is actually this one. Now, typically what we did was, for the pressure terms, we said that this pressure is on the east face minus pressure on the west face. That was done when you had the collocated grids, a nominal control volume for everything. But this time, if I want to talk about the eastern face of this green control volume, then that actually comes out to be the eastern capital E node, because the capital E node coincides with the eastern face of the X momentum control volume. So I would rather, based on the convention that we have in this figure, this will be P on the capital east face minus P on the P on the capital E node minus P on the capital P node. Subscript for P in where? In the equation? That's just pressure. So I have told that this is the pressure control valve. Alright. Now in this case, if we look at how to specify the mass fluxes, so for example, if I want to specify the mass flux on the eastern face, now when I say eastern face, this is the eastern face of the X momentum control volume. So we'll have to be, that is actually one of the major issues with staggered grid, that you have this confusion as to what denote what. So sometimes it is much better to write, rather than the eastern face, we just write f of I plus 1 upon j. So then we are clear that, because indexing is unique. So this capital P we called I comma j, and then this U is defined on I plus half comma j, and then the capital E is at I plus 1 comma j. Alright, so this flux, which is on the eastern face of X control volume, eastern face of X control volume, how will we specify this? So we used to specify this as a center averaged earlier. Right, so this flux is actually given as U on the eastern face times delta Y, eastern face of the X momentum control volume, and that earlier was not known, because you knew the U values at the center of the nodes. Right? How will we specify this time? Still have to average it, right? Because if you look at the green control volume, then the mass flux on the so we need these mass fluxes on the faces of this. So we will have to find this. So we'll have to average it, right? But if for some reason you require the mass fluxes on the faces of the nominal control volume, that is the pressure, that is known directly. So what we're trying to say is, when we write the semi-discretized X momentum equation, on this green control volume, then we require the fluxes on these faces. That is what is meant by capital F subscript F. The eastern face is the right face, western face is the left face, northern is the top, southern is the bottom. So to get the flux, because we need this flux, one, we need this to specify the direction of upwind, because when we specify UF, let's say U east, the U on this, then we'll have to figure out what is the direction of flow. Is it left to right or right to left? Right? So we'll have to specify this. So these fluxes, you have to figure out how to write them. We cannot just copy the techniques from the collocated grids, because there the indexing and the quantities were defined at different locations. Any questions? Now, when dealing with the continuity equation, so let's say we have the continuity equation, there also we will end up getting these fluxes, because we get, if you discretize the continuity equation, which is given as divergence of velocity. So when you integrate this over the control volume, this gives you u dot d gamma, right? And this continuity equation is discretized on the nominal cell, which is the one which has capital P as the center. So when we do this, let's say for the eastern term, we'll have a summation which will include one term as u east times delta y. So if I want u on the eastern face of this nominal cell, how will I get that? So nominal cell is this one. The one which has capital P as a center. So if I need the eastern face velocity, well, that's already known directly. So this time I do not need to do any sort of interpolation to get this u east, and u east times delta y is actually the mass flux. So the mass flux on the boundaries of the nominal cell is known by definition of the staggered grid. So that makes the life a little simpler. Okay. So just be careful about these things when you are writing the final equations. So let's move beyond the discussion on staggered grid, although we'll be using this in our discussion in the implicit methods that we'll be talking about in the next few lectures. So it will reinforce the ideas, but this is typically the main idea. So we'll be using this equation that we have just written. And if you're talking about a fully implicit scheme, so let's start with fully implicit. And try to sort of do a difference between what we are writing now and what we have solved in the past in our semi-explicit method that we had. I'll also try to highlight the differences. So in a fully implicit scheme, if I look at this general form, let's call this equation Z. So in equation Z, what we do is we define every term at n plus 1th time. That's what implicit means. Fully implicit would mean that everything is defined at the n plus 1th time. So this equation would then look, of course this is the transient term, so this requires a difference between n plus 1th and n. So this time the mass flux F is also defined on the n plus 1th time, same as UF. So this is the x momentum equation. Now this y momentum equation is going to be defined at different indices, because y is the y control volume is the one that is the red one. So the index of the y control volume is going to be I comma j plus 1, j plus half, sorry. Just remember that this diffusion and this diffusion, they're not the same terms, because the one above is for the diffusion of u and the one below is diffusion of v. So in this term, this amounted to nu times gradient of u dot delta gamma f. Right, so here we'll have nu times gradient of v dot delta gamma f. So they are different, except that I'm just using the same convention f du of f on f, but they're diffusion of different quantities. Oh, sorry, yeah, thank you. So how is this different from the semi-explicit method that we have discussed in the past? So let's visit term by term. Of course, the transient term is still the same, there is no difference. What about the, let's talk about this equation. So what about the convective terms? At what time were they defined? N plus 1th or nth? In the semi-explicit method. They were all at n, so this was n. What about pressure? Pressure was at n plus 1, right? And what about diffusion? N. So this is the difference between a fully implicit that we have here and the semi-explicit that we saw. And that is typically what you do, right? So in explicit techniques, you tend to write everything except the transient term at nth time, except that we use pressure at the n plus 1th time for reasons that we have already discussed. But here we will have everything at n plus 1th time. It's a fully implicit technique. Now what about continuity? So let's write continuity as well. So this is what continuity equation becomes. So the first equation is defined at the x control volume or x momentum, so I'll call it at the u control volume, and this is at the v control volume, and this is at the nominal control volume. Nominal is the one which has capital P as the center, because we have to understand where we are, on which control volume are we integrating the equation, because ultimately finite volume is obtained by integrating the equation over a control volume. So they are different for different equations. So what about our semi-explicit technique? How was that different from this continuity equation that we have written here? Was it at n or n plus 1? How many people say n? And how many say n plus 1? It was n plus 1. So if you recall, we had discretized the continuity equation on the n plus 1th time, because we said that the n plus 1th velocities that we are getting should satisfy continuity. Because if we do it on nth, that's already true, because you already have the un and vn. So they are satisfying continuity, so there's nothing to obtain from that. But the new velocities that you are finding should satisfy the continuity equation. So this is fully implicit scheme. And then there is also something called a semi-implicit scheme. Like we had semi-explicit earlier. Remember, these are names. Okay? They do have some correspondence with what they mean, but these are just names to identify the different forms of equation that we are solving. So next is semi-implicit. So this is exactly like the fully implicit, except that the mass flux is discretized at the nth time. That's the only difference. So I'll just highlight this. Of course, the continuity is still the same. So we have summation over S, f n plus 1 over the face is equal to 0. There is no difference in the continuity equation. I will not write this control volume again and again. So we'll give them numbers. This we'll call 1, 2, and 3, because we'll be solving the semi-implicit equations in the next 2 lectures. So I have given them numbers. Others are not being numbered for now. So we have the U equation, we have the V equation, the U momentum and V momentum equation, and then we have the continuity equation. So when we had written the equations in the semi-explicit method, what was the problem that we faced for which we had to propose a predictor-corrector algorithm? P was defined, P on the right hand side is required for n plus 1th time. On the semi-explicit method, apart from P, everything was at nth time. So we were in a problem that we had to figure out a way to find Pn plus 1. So we proposed that predictor-corrector algorithm where we started with Pn, we got U stars and V stars, and from there we corrected them using the continuity equation to get P prime, U prime and V prime. So we'll follow a similar approach here as well, because we have the same problem that we need Pn plus 1, but there is no direct way to obtain it. Okay, so we'll use an iterative approach, but we'll discuss this approach. So this statement will not tell you what we are going to do, except that the approach will be iterative, but we'll discuss this as we go along. Now you may be wondering, why did we discretize the mass flux terms at the nth time? There should be some benefit, right? Otherwise, why would we do it? So there are a couple of benefits. So let's discuss them. So first is linearization. If you look at the convective term, which is let's say this one, capital F times UF. Now capital F also contains a UF in it, because capital F is nothing but given in terms of the velocity, so it will have a UF in it as well. So you get a non-linear term here, UF times UF, and that can create problems because we are trying to write this as if you see the final form, we try to write a linear equation out of it, but this will not be a linear equation because you have U times U. There it becomes non-linear. Solving that becomes difficult, sometimes impossible. So if you instead write the flux term at the nth time, then what will happen is that you will have un at the face f multiplied by u at n plus 1. So the unknown that we have, the un plus 1 on the face, will have coefficients which are known, so it becomes linear. And that's a very common strategy being used in solving nonlinear equations numerically, that you linearize them. So this is one way to linearize them, that the coefficients of these which contained those terms can be written at the previous time. Now of course, that will have some restrictions on the way you solve it and so on. You cannot take large steps while solving it. You have to solve it iteratively until it converges. So that will definitely be there, but at least it allows you to proceed with the methods that we already know.
So we can use the velocity at n time and the flux at n plus 1.
Well, that won't work because here what's happening is that the right hand side velocity that we have is sort of the term that we are trying to solve. That's the unknown here. And the fluxes are you are saying that why don't we do the opposite thing, right? It doesn't work. Let's give the short answer here, because F fluxes are the coefficients here, and the one that you're trying to solve is the unknown velocities. Think in terms of solving a scalar equation, where like the 1D wave equation, for example. So there the velocities were there, and then you had a quantity called phi that was being convected. So think of in that terms. So the quantity that is being convected is the one which is UF, and the fluxes are the coefficients. So if you think in terms of parallel with a scalar equation, it will make sense. And we are taking our motivation from those methods. Next is it helps us to decouple the U and V equations. So let's look at the equations again. So if let's look at the form that we had earlier. Let's say this one, fully implicit. So here we have these flux terms. So if you expand them, let's say expand the flux term in the x momentum equation on the northern phase. So the northern phase flux is going to be V on the northern phase at the n plus 1th time, because here it's everything is at the n plus 1th time. So what we see is that the V velocity at the n plus 1th time on the northern phase comes as a coefficient in the first equation, but that is going to come out of a solution of the second equation, and the second equation flux will have contribution from the U velocities on the eastern and the western phases. So what we are seeing is that a coefficient of one equation is actually an unknown in the other equation, and vice versa. So we have to solve them separately. They are coupled to each other. So what we have done is, if you define these fluxes on the nth time, like here in the semi-implicit method, then the coefficients are all at the nth time. They're all known. So if you look at the U momentum equation, V velocity at the n plus 1th time does not appear at all. Similarly, for the second, the V equation that you have, U at the n plus 1th time does not appear in this equation. So they can be solved separately. That's a very important thing that helps us computationally make things much easier. So we are decoupling them from each other. Okay. Next is it helps fix the direction of upwind. Now in upwinding, you need the sign of the flux term. So is the flux term positive or negative? Because that defines what is the upwind cell. So if it's positive, it's the left one. If it's negative, it's the right one, the upwind. Right? So, but if the fluxes terms were at the n plus 1th time, they are unknowns. How can you fix the direction of upwind if you don't even know what the direction is? Okay. So if you define the fluxes at the nth time, which are known values, now you know should I be using the left or the right cell in the when upwinding the unknown, which is this one. Is that clear? So these are very important three reasons for which we solve semi-implicit equations, and in fact the solvers that you see, they solve mostly the semi-implicit equations, not fully implicit, because solving fully implicit has many challenges associated, as we have discussed 3 of them here. Right. So the question is now again, pressure. As we have written here, that there is no direct way to obtain Pn plus 1. So what do? Well, we use the same predictor-corrector approach that we had earlier. Okay, so you predict, you start with a pressure that is not Pn plus 1. Let's say you start with Pn. So you get u stars and v stars, and then you use the continuity equation to correct them using p prime and u prime and v prime, and then you move forward. It's same idea, but implemented a bit differently because now we are solving implicit equations. They're not explicit. So let's highlight what is different here. So what we have done is, instead of Pn plus 1, because we do not know Pn plus 1, we have used a guessed pressure P star. So we'll discuss how we guessed. Earlier we had used Pn. So we'll discuss how we guess it, but we have guessed a pressure. So if you guess a pressure P star, which is not equal to Pn plus 1, then you will get u stars and v stars, not un plus 1 and vn plus 1. So if I replace this P star with Pn plus 1, I get un plus 1 and vn plus 1. But if I don't do that, then I get different velocities. So these velocities are called u star and v star. So that's the reason all the instances of un plus 1 become u stars. So similarly, the diffusion flux, which was defined at n plus 1th time, is also written at star, because diffusion flux contains velocity terms. So they are all they're all starred values. And that is exactly what we did in semi-explicit method as well, except that the un plus 1 and vn plus 1 only appeared in one term, that's a transient term there, because it was explicit. But here it's implicit, so it appears again and again. So the way we solve this equation, given that you know the P star value to start with, you start with some guess P star value. So how will you solve this for a given P star? You will have to iterate, right? So now this discussion can get a bit complex in the sense that there are too many iterations happening. So just try to understand the discussion in the context of the present equation. Don't try to go back and rethink. We'll combine, we will bring together the ideas towards the end in a good, nicely written algorithm. But try to understand ideas while they are being discussed for a given situation. So to solve these equations for known P star values, or guessed P star value. So P star is known here in this equation. Now we want to solve for U stars and V star. Let's say U star in the equation 1a. But U star appears at multiple places because it's implicit. That's what implicit means. That you cannot write an unknown in the form of knowns. You have to write an equation which is some sort of a linear equation, a system of equations. So this will result in a system of equations. If you write this equation for each and every point, you'll get a matrix. But what was the problem of getting matrices like this for 2D or 3D systems? It was not sparse. I mean, in the sense that you had banded matrices. When we had discussed this in the context of heat conduction problem, what we got was, we got banded matrices. So that's the reason we went to an iterative technique. We had a good discussion on the iterative methods such as Gauss-Seidel with the relaxation and solving it on lines and so on. So that was all discussed because solving this directly using matrix inversion was expensive. Same problem is here as well, because now you have an implicit equation, so you have to solve it. So for that we'll use iterative methods. But how do iterative methods work? Iterative methods start with a guess for the thing that you're solving for, and it has an iteration formula. It improves the guess sequentially. So here what we do is, we use this kind of an iteration. So for instance, what we could do was, we could start with U star equal to 0, because I don't know U star, right? So let's take U star equal to 0. So U star old values are 0. And I substitute that here. So U star old is known, and so is P star is definitely known here, it's a guessed value. So you get U star new. That's one step in the iteration. Now you make U star new as U star old, and then you have a better estimation for U stars. So you keep doing this. That's the iteration. You keep doing this until you meet a stopping criteria. And the stopping criteria is that U star old and U star new become the same. So when they become the same, you have reached the actual solution to this predictor equation, because it's still for P star. P star are guessed values. So implicit equations are solved in an iterative method until you converge to the solution of this equation. So this is the iteration formula. So similarly, we can write the iteration formula for V equation as well. So let's summarize this. So pressure, let's say you know the velocities at the nth time and the pressure at the nth time as well. So the exercise is to find un plus 1, vn plus 1 and pn plus 1. So in this equation what we do is, since we have to substitute a guess value for pressure, I'll say let P be Pn. So I substitute that and then I get U stars and V stars. To get U star and V star, I have to start with some initial guesses, that is old values. So I say that rather than choosing 0, which will lead to a slower convergence, let's start with a value which is equal to un and vn, because they will be closer to the, because see, if your delta t is small, then there will be a small change in the u and v velocities. So rather than starting from 0, which will require you to move from 0 all the way to the solution, you start with un and vn. So un and vn will be the first guess for in this iteration. And then you keep iterating with this pn value until you get u star and v star, which are the solutions to the equations 1a and 2a. Once you do that, then you have obtained the solution to the first iteration with the guess Pn. So this is where we'll have to read this line. So it says we use an iterative approach to get Pn plus 1. So we'll discuss this in the next lecture again, but do think about it that we have done all this iteration for predictor equation just to get u star and v star for a given value of p. Now we'll put this inside a bigger loop where we improve. So whatever value that we have got of u stars and v stars, we'll use that to improve the guess for pressure. So we'll have a new p star value. But for that we need to include the continuity equation at some, because these u stars and v stars we have obtained do not satisfy continuity till as of now. Why should they? Because you have solved them using a pressure which is at the nth time, a guess pressure. So now we'll have to include the continuity equation with it so that we can get a method to improve the guess for pressure. And we'll keep doing that again and again until we get Pn plus 1. Okay, so we'll discuss this further in the next class.